I am Jeroen, and I welcome you to my lecture series on computer and network security. In this video on message authentication, I will talk about the most known and used family of cryptographic hash functions, secure hash algorithm or SHA. And the secure hash algorithm family of cryptographic hash functions is by far the most widely used one, mainly because any other cryptographic hash function proposed to date has been found to be insecure. It was first standardized by NIST as SHA-0 in 1993. However, in 1995, some problems were detected, some security issues, and it was replaced by SHA-1. In 2002, an improvement called SHA-2 was proposed, and in 2005, NIST decided to phase out the use of SHA-1 in favor of SHA-2. In 2008, some extensions were proposed with larger, different-sized hash values. And finally, in 2012, NIST concluded a competition to develop a replacement of SHA-2 referred to as SHA-3. And here you see an overview of SHA-1 and SHA-2 and their characteristics. SHA-1 had only a single variant with a hash size of 160 bits. It supported messages up to 2 to the 64 bits. SHA-2, on the other hand, has quite a few variations. You have SHA-2 224, 256, 384, and so on. However, all of them are actually based on two of the variants, SHA-256 and SHA-512. SHA-224 is basically SHA-256 truncating to the 224 leftmost bits of the hash value. The same is true for the others, which are all based on SHA-512 and taking the T leftmost bits. The later variants of SHA-2 support actually messages up to 2 to the 128 bits. A major issue with both SHA-1 and SHA-2 is that they are susceptible to the so-called length extension attack. I will explain this attack in the next video. And let's take a closer look at how SHA-2 and specifically the 512-bit variant works. As I mentioned before, the message can be at most 2 to the 128 bits. This is because the message will include, before being hashed, the length of the message in a 128-bit field. On top of that, it includes some padding, a 1 bit followed by zeros, to make sure that the total message is an integer multiple of 1024 bits. The message is then split into separate 1024-bit blocks, M1 to Mn. Subsequently, each of the blocks M1 to Mn is processed sequentially. Starting with the first block, it is processed by the block function f. Subsequently, it is added to the initialization vector h0, which is a constant value. This produces the first output block, h1 of 512 bits. This block is then used as input to process the second input block M2 to produce H2. This process is repeated until the last output Hn is calculated, which serves as a 512-bit hash value. These intermediary outputs H1 to Hn-1 are represented by 8 words of each 64 bits. They are referred to as A, B, C, D, E, F, G, and H. And let's take a closer look at how the block processing function f works. It takes place over a total of 80 rounds. In each round, the intermediary inputs and outputs are represented by 8 words of 64 bits each. As I mentioned before, they are represented by A up to H. The initial values of the words are equal to the output of the processing of the previous block. So the intermediary hash value HI-1. During each round, the 8 words are combined with a round word W and a constant K. The constants, the 80 constants, are the same for every block, while the word rounds are derived from the message block MI. So this message block MI of 1024 bits is transformed into 80 64-bit values, W0 up to W79. After the 80th round, the output is combined in a word-by-word addition with the output from the previous block HI-1. This result is then calculated modulo 2 to the 64th, and these 8 words that result from it are the intermediary hash value HI. And here you can see how in each of the 80 rounds, the 8 words of 64 bits are combined with the value W derived from the message block M and the constant K to produce the 512-bit output of that single round. I won't go into too much detail of the specific operations. However, it's important to note that 6 out of 8 words are simple permutations, namely the ones marked in gray. So output words B, C, D, F, G, and H. Only output words A and E are the result of substitutions, where they depend on the input words, the value W, and the constant K. The operations make use of a combination of right circular bit shifts, XOR, and logical AND. The only remaining question is how the input words W0 to W79 are calculated out of the input block MI. Specifically, the first 16 of these words are directly derived from MI by splitting the 1024-bit block MI into 16 64-bit words. Subsequent blocks are derived from previous words. In general, word WT is calculated out of WT-16, WT-15, WT-7, and WT-2 by doing an addition modulo 2 to the 64th. The second and fourth input word are transformed using the sigma 0 and sigma 1 functions. These functions perform a combination of right circular bit shifts, exclusive ORs, and right bit shifts with padding by zeros on the left. To end this video, I have an exercise for you. To calculate a round word W16 based on a simplified version of SHA-2, where the block size has been reduced from 1024 to 128 bits and the word size has been reduced from 64 to 8 bits. Here you can see the block, the message block of 128 bits represented hexadecimally, and a summary of how to calculate a word. Good luck! In the next video, I will talk about the length extension attack and the newest member of the SHA family, namely SHA-3, which is resistant to this type of attack.